Welcome to our session. Our last topic is time series prediction implement with Python. We have two speakers. One is Trudie, the other is Hsuanyo. Trudie is now studying in National Taiwan University. Although she is still a student, she has been working in an IoT company as data analyst engineer. Our next speaker is Hsuanyo. Hsuanyo has worked in Monbago as a machine learning modeler. Both of them are interested in machine learning algorithms, especially for the time series data. As a financial modeler, I really look forward to your sharing. Okay, anyway, let's welcome for the Trudie and Hsuanyo's presentation.
Okay, hello everyone, I'm Trudie, and today I'm going to talk about what is how to implement time series by Python. And at the beginning, I want to talk what is time series. Time series, to put it very simply, you just record the value in the fixed interval, so you can call it time series. Very simple. And normally we decompose the time series into 4 parts: trend, cyclic fluctuation, seasonal fluctuation, irregular fluctuation. And I'm going to use the picture to help you understand how these 4 parts. And you can see the value growing very slowly. It's just, we can call it trend, increased trend. And cycle is cyclic fluctuation. You can see the peak and valley pattern appear again and again. And it usually accompanied with the long trend. And seasonal is similar to the cyclic, but its repeat period is only 1 year and associated with the natural events. And irregular is, aside from the 3 parts, the remainder is irregular. And there is a lot of methods to implement time series: OLS, GLS, whole winters, wavelength analysis, Fourier transform, SVR neural network, a lot of methods. And today we chose these models to introduce you, and including Hive and SDA. And the SDA part, Yo will talk you later. The following part, I will talk about ARIMA+SVR, and Yo will introduce the SDA model later. I want to use only 25 lines Python code, to implement the ARIMA+SVR. And I will going to talk about why I chose hybrid model ARIMA+SVR and how to implement it. Why I chose ARIMA+SVR. I can remember the scenario is that there's an IoT report platform, and the device will send their report in real time. Our target is to predict the number of activated devices online. We tried many simple and linear models, but the performance of the models was not good enough. Thus, we need more complicated model. After research, I found that ARIMA is a popular model in time series and often used in econometric. But we can say ARIMA is still a linear model, so we decide linear model. So we decide to add another powerful model, SVR. And there was a lot of practice to implement this hybrid model in the real world, and the performance are good for. For example, traffic flow analysis, stock forecast, and petroleum mining, etc. Since we choose ARIMA and SVR. And to put it simply, ARIMA responds for the linear part, and the SVR is responsible for the residual part. ARIMA for the linear part, I say it's just like capture the whole picture, and SVR responds for the tuning the detail. You can see this is ARIMA for the whole picture and SVR for the detail part, tuning the model. But I don't have many time series analysis experience at that time. I'm not expert in statistics and econometrics to decide the ARIMA parameter. ARIMA has 3 parameters, P, Q, R, and it's very, you have to verify it is stable, so you can put the data in the ARIMA model. And you have to use the AIC, BIC to choose the best model. It's a long training process. So I use the Python package to help me to automatically decide the parameter. I use the R have one method to automatically choose the ARIMA parameter, but in Python we are very easily to use the R through the rpy2, and use the at the beginning you import the rpy2 package, and next step activate it and get the data. And when we use the ARIMA model, we have to import the R package called forecast and stats, and use the R object to access the R model called auto ARIMA, and feed it, put the data in the model. And the model is just very simply established. And the residual part for the SVR, you can call R object called residual. And next step is SVR. And when you want to put the residual in the SVR, you have to transform the residual by embedded dimension. And these 2-3 lines of code is to transform the residual and put the residual in the SVR. And you just finish the ARIMA and SVR model. And in the implementation, I want to, And when we try to decide the SVR parameter, we can simply use the grid search in Soocii package. It will decide the best set of parameter of SVR for you. And in the real world, when we want to predict the model, when we want to predict, you have to save the model first. So we use the Pico. It is a package that helps you serialize the training model. And the next time when you want to prediction, you just use these to load the model. And in real world, we made some problem. Is that because the IoT device send a report, sometimes the machine will fail, and there is some exception event. So we have to detect the exception first. So the ARIMA SVR part just have to model the normal part, and exception modeling have to another model to model it. So the problem we encountered that is when you want to use ARIMA plus SVR, you have to do some serious analysis to detect the exception first. And another issue in time series is that the cross-validation. Traditionally, we randomly split the training and test data by randomly split it. But in time series, the order of the data is very important. So you should be very careful to use the cross-validation. And this is my part.
Okay, now I'm going to talk about this analysis the complex factors by static noise in autoencoders in time series cases. Okay, In my sharing, I will separate into 3 parts. The first one is the case descriptions. And I will briefly introduce the stack-denosing autoencoders algorithm, and I will give you 2 examples of the experiments. And then the last part, I will talk about the challenge that I implement in the real world. Okay, so originally, I want to solve a problem that I want to predict the number of the people in the office. So I defined it as a regression problem, and I think that this may have some factors influence people whether they want to stay in the office or not, like the outside temperature. If it is high, and you will like to stay in the inside. And I read some papers and found that there's a model called stack-denosing autoencoders. And I use it because that, first, it's a nonlinear algorithm. In other words, it can, the model can be trained by the multi-factors. And the second, the model can strengthen the weight of the effective parameters in the dataset. And third, it can use the shortened dataset to forecast the future. And the last is faster and more accuracy than the shallow algorithms if you have huge volume of dataset. Okay, and I use these 3 packages for my experiments. The first one is Keras. It's a deep learning framework, and I use the TensorFlow as the background of the Keras. And then I use the IPython to visualize the result. Okay, and I'm going to introduce about the stack-denosing autoencoder. It's also called SDA. It is a deep learning model, and it has 2 stages of this model. The first one is pre-training process, and the second one is fine-tuning process. The pre-training process, you can think it is like a feature selection part, and the fine-tuning part is focused on supervised learning. Okay, and the pre-training part is that I use the raw data and give the noise layer to noise the data, and use the noise data to train the neural network. And if you finish the training of the hidden layer, you can append it into a list. And then you use the hidden layer as the second and the third time of the training. So you will have about three hidden layers in the list. And let me show you some codes. I implement on the Keras of the version 0.3, and the TensorFlow is 0.8. And you can see that the first thing is I add some Gaussian noise and drop out there to show my noise layer, and combine the encoder and decoder into an auto-decoder layer, and training the model, and then append into the list. And then you can see there's a for loop containing three things, and the for loop will loop about 3 times. So this will append 3 encoders into the list. And then we come to the fine-tuning part. Okay, the fine-tuning part is easy. It uses this, the fine-tuning part feature out these 3 hidden layers as the hidden layer of the fine-tuning neural network, and add the supervised layer in the rest of the neural network, and there's comes a result that it can train your data in supervised way. Okay, that's a code. And first you fetch out the encoders in the list and train the model. Yeah, it's easy. And I'm going to talk about 2 experiments in in the UCI dataset. The first one is UCI SML 2010, and the main target is hope to predict the indoor temperature. And I use the 6 parameters to predict the indoor temperature. And you can see that the result is the mean average percentage error is 13%. In other words, the mean average error of this model is below 1 Celsius degree. And the second experiment is talks about the predict the global active power, and the datasets use the UCI individual household electric power consumption. And I use the 9 parameters to predict the global active power. Also, the mean average percentage error is below 5%, and it means that you can predict the voltage. The mean average error of the voltage is below 0.5 voltage. And that's the red one is the original one, and the blue line is the predictable one. And we will put our PowerPoint to the hackpad later, so you can see more clear. Okay, so last thing is I want to talk about is the challenge of the implementation in the real world. The first thing I want to talk is that you have to prepare an appropriate data set for the model. What I mean is that you need to focus on how to find the effective parameters for training a model. This is very important things. Or I would like to say this is the most important things for you to forecasting the future. This is because that if you use the not efficient, inefficient parameters, or you use the junk parameters, they will junk in, junk out, so you won't have anything that you expect in the output. And the second thing is that the problem of the Keras and TensorFlow packages. We all know that Keras and the TensorFlow is the novel package of the Python, and they just released in the end of the last year, so they are very new. And yeah, it comes out the problem. If you want to upgrade your version of the TensorFlow and Keras, it all face some problem, some unreasonable bugs in there, and you have to rewrite your code again to run on the last version of the Keras or TensorFlow. So it is very, I can say that it's not very friendly for the developer, but it's really nice to use it because it's the TensorFlow backend is fast, and yeah, and the Keras is very friendly to use. So there's some problem that I faced when I implement in Python. Okay, the last things I want to talk about is what I thought to SDA. SDA is like an energetic and vigorous horse, and but it's undomesticated. What I mean is that if you want to tend it as your horse, as your own algorithm, you have to pay a lot of attention on it. You have to really accompany with it for a long time and deeply know about how to use it and what is the mechanism inside. So they can help you to understand better, to use the algorithm, and you can have a better performance to use the algorithm. So that's our talk, and thank you for your attention. And we hope that you like our speech. Thank you.
Okay, anyone has any question? please raise your hand. Okay, please.
Hello. When it comes to time series, I think it's natural to think about stock data. Is the method you mentioned universal to all time series, including stock data? If not, what's the limitation?
You mean the stack? Oh, stock. Okay, stock market, right?
Yeah, stock.
Okay. I think that if you choose the right parameter to put into the algorithm, I mean the right parameter is suitable for the algorithm. So there's comes a result that every algorithm has a specific type or specific way to have the parameter because they use the different mathematical models to implement it. So I can talk to you that I can answer your question that yes, it can apply in the stock market, but you have to choose the right parameters to train the model. And if you choose the right one, okay, the performance will very well, and you are very lucky. Yeah, thank you for your question.
Okay, anyone has any question? Okay, if no, let's thank for Trudie and Hsuanyo's presentation.